Okay, guys, welcome back to class. So we have a Kahoot. So please take out your phone or go visit the page. So you can go to www. And join. So I'll give you guys a couple minutes to join. So what we'll do is the support group will write a Kahoot quiz for every week, and we'll play the Kahoot quiz in the following week, okay, at the beginning of class. People often ask me, is there any prize for winning the Kahoot? And the answer is no. Okay, so sorry about that, but I hope this will be a way of just revising what happened the last week. So I'll give you guys another 2 minutes or so, and then we'll start. Anyone not in yet? Everyone who wants to participate? Okay. We'll give you another minute or so. We have, I just wanted to make sure everyone is there. On the days which we have you're assigned to lecture, your lecturing team should prepare for about an hour and a half. Okay, no more than that, because I love to interrupt with discussion and sidetrack you guys. Okay, and I think it's better done that way so we can discuss. It's not a lecture. Okay, so we want to go through that. And because at the start of class we'll have Kahoot. Okay, somebody from the support team should be on that, and somebody in the support team should also go over the scribe work. So you remember the scribing work that you're supposed to do. Okay, go to bit.ly, right, and then put in the class, and then scribe, right? Then you go to the scribing document. Hopefully that's correct. Let me turn off the sound here. Okay. So we have to always clean up the document that's written here, all right, during class. Okay, try our best to do that, because we're trying to make again something for the public and other people learning language models to hopefully learn a little bit from. We don't expect it to be as polished as a lecturer spending a lot of time on course preparation, right? But hopefully by having 30 plus people in the class together, we can do the job fairly well. Okay. So without further ado, let's play Kahoot. Are you guys ready? Yeah? Okay. Okay, the first question. Emergence is a blank change that arises from a blank changes. Okay, so this was a part that Michael gave us before, right? To say that emergence is defined as a change, a qualitative change that happens as a result of quantitative changes in a neural network, for example. Okay, so good. Many of us got that. So how do I go forward? Okay. So Marcus is in front. We have H100, a very expensive card, in second place. Suvin in third place. Okay, a multi-select question. Name the factors that have contributed to the growth of AI intelligence. We have data quantity, data quality, model size, and hardware. Okay, from Michael's slides, we had the first three that are highlighted. Data quality is definitely there, but it wasn't in one of the factors that Michael highlighted. I think, Michael, I wrote these quiz without your help. So maybe you can debate whether you agree or not, and that's fine. Okay, I think we all know that quality is an important factor, but definitely when we hear about people training large language models, people is always concerned about amount of data, right? Even though we know that quality is a very big factor as well. Oh, okay, and JX has come out and see how is going up. Okay, we see how is going to do. Third question. What do we think LLMs can't learn from next word prediction? Can they learn factoid answer question answering? Can they do open-ended arithmetic? Can they do summarization? Machine translation? What do we think? Okay, so that's right. Okay, so I think we have an AI transcribing the meeting. So hopefully that'll be helpful. Okay. So Marcus is still in the front with several competitors close behind. Multi-select again. Okay. Why do we use the transformer architecture anyways? Because it gets good results. Because it processes context sequentially. Because it models context. Because it can be easily parallelized. With the multi-select, you can select more than one. Try your best. Okay, it does process context. It doesn't do it sequentially, right? We all know it parallelizes it. It's not like a BIOS-TM or LSTM or RNN that runs left and right first to build up state. So that's the only difference. We use it, of course, because we get good results. So I know, like in academia, we like downplay that, good results. Who cares? We want knowledge, not data, right? But definitely people use it because it gets good results. Okay. Okay, Marcus still hasn't been dethroned. Let's keep on going. BERT is what type of transformer model? Okay, is it transformer based? Maybe it's not. Is it an encoder decoder architecture? Is it decoder only, or is it an encoder only model? It's an easy question. You guys have to be on encoder, right? Okay. Oh, okay. It's not an encoder, right? It's encoder only. We encode everything so that we can use the word vectors for BERT, right? Okay, so we apply it to a downstream task. That's the decoding task, but not the encoding task. Okay, so let's be clear about it. Again, there are some undergraduates and other students in the class who have very little basis for the math, and that's okay. I want to let you guys know it's okay if you don't get everything, all right? You can sit in the middle and then learn about large language models and come back and get the math later, or apply what you understand about it and do well for this course because it's pass fail anyways. Okay, that's not the important point. The important point is exposure. Okay, so don't feel like you're obligated to understand everything. So if you have problems with any of the quiz, or you completely, like the first lecture was way above your threshold for math, you can just write on the general channel, ask for help. Somebody in the class will probably help you and say, okay, this is a good Medium post, that's a good YouTube lecture video, some general resources to help you out, okay? Okay. GPT is what form of transformer model? Same options. Is it transformer based? Right. Encoder, decoder, encoder, or decoder only? Okay, so it's a decoder only model, right? We use whatever's already encoded and we decode it for a specific application. Okay. Clyde and Hannah come up on the scoreboard. Let's see how we're doing for the second to last question, multi-select. How does instruction fine-tuning differ? It should say differ from reinforcement learning from human feedback. Are they essentially the same? Instruction fine-tuning emphasizes zero-shot tasks? Maybe RHLF emphasizes the reinforcement learning aspects? Or they're just different? Actually, they're all correct. Yeah, so everything is correct. Okay, so I think, I did some research on this and I think they're pretty much the same. They are just gone by different monikers, and maybe in a couple of years, people only refer to it with one thing. That depends on how much marketing dollars you throw at it. Maybe that's what the system will call it, right? They are different to certain small degrees, but they're basically the same idea. You use some type of way of ranking from human feedback, which types of outputs that you prefer, and then you optimize against that, using some type of reinforcement learning algorithm. Okay, so if you were bewildered about this, yeah, we need to study more, right? Because there's a lot of terminology and they, sometimes mean the same thing, sometimes not. Okay, our NVIDIA processor has called back up to the front. Okay, our last question is what key lesson did we discuss when discussing the VIT paper? Quantity matters, quality matters, transformers are the best. Both data quantity and quality matter. Okay, so Michael shared with us that changing the type of data and the quantity of the data mattered a lot to make vision transformers work, right? Because we saw that the previous work was using ImageNet, which is just very small quality pictures, naturalistic images of certain types. That didn't really work very well, but changing the quality and the quantity of the data made vision transformers succeed. Okay, so let's see who's winners for today. H100, JX, and I guess we expect it, right? Marcus, let's have a hand for all of our winners tonight. Yes, we want to leave. Okay, so again, the support group is supposed to create a Kahoot. There are instructions for doing that. Okay, so as you guys, as the support group for lecture 2, please take note of what your lecturers tell you about. Again, I hope that the lecturing team will be able to put out which papers, roughly the structure of what they're going to talk about by next Tuesday, so that by Friday, we can have it all together, okay? So the Kahoot for this week's lecture 2 will feature in lecture 3. Now, we all know polling day has thrown a wrench into our outline. I haven't found a time yet to figure out where we're going to be for lecture 3, but I will let you know, okay? Maybe it will be on another day next week, okay? Maybe we'll just say, you know, well, we'll forget 1 week and then we'll push into recess week, but I've been told we're not allowed to do that because we care about your well-being as lecturers. And so we're not allowed to impose anything on reading week or recess week. So either we'll have one less lecture or we'll have to squish it in somewhere, okay? So that's all I have for you, and we'll turn it over to our lecturing crew now, okay? So can I have the lecturing crew come up, please?
Hi everyone. So yeah, I think we are the team like to give the second week's lecture about the adaptation of large language model. So yeah, so it's beginning by me, start by me. And yeah, here's our team: Hengchang, Ting, and Xiao, and Yanxia, and Yajing. Yeah, and we will give the following topics one by one, or not topics. Actually, I will give you an outline first. So firstly, is that why we need to adapt the language model. Yeah, as all of you know, the language model can learn can grab some synthetic structure and lexical pattern from words, but it's probably not that useful for some specific tasks. So we need to adapt them. And yeah, we will give the following some solutions. So for example, from the relatively simple probing the technique, and then to some fine-tuning techniques, and then probably I think it's the most people concerned about is how to tune the large language model with a lightweight method. Okay, so the firstly, why adapt the large language model in case some of you may not have such background? So I will start from this slide. So the large language is language model. So large language model actually is just a small subset of language model, right? So the language model, we expect the language model to remember, as I said, some lexical pattern and some word and word relations, and some other stuff. Actually, I believe most of ours don't know what the language model actually remembers, but we want them to remember as many corpus as possible. Like, yeah, and actually from now on, at this point, the language model gives us positive reflection on that. And but if we want them to do some specific task, for example, we give them some specific document and let them to predict something, for example, the human preference, for example, the semantic analysis task or some recommendation task. So this is all a very specific task. So if we like come up with this task, probably this language model is not able to handle them. So they will say, oh, I have no idea what you are talking about. Probably because of the formats, or probably because of the distribution of the text is totally different. So actually, some of you may say, oh, the prompting may work because the prompting is super strong. So I probably can ask, for example, when coming the summarization, the text summarization task, I can ask the language model to say like, oh, summarize the following text for me, and the language model probably I can summarize the text for you. But when you come up with another task, for example, as I said, the total different task, like the recommendation task, to predict something, to do some classification, the language model is not good at this one because they never be taught such skills on some specific downstream tasks. So as I list here, actually this is borrowed from Prof. Percy's slides. So, for example, downstream tasks, natural language inference, and the question answering and the summarization, they are all very specific tasks. So the language may not very good at this one, and so we need adaptation. So here is a more specific example of the natural language inference. So natural language inference, from my understanding, is basically a classification task. So, for example, we have promise, I have never seen an apple that is red, and we have a hypothesis that I have never seen an apple. And we expect correct outputs that they are not in, the relation between them are not in no impairments. So such task, you can imagine that if we directly ask the language model, they probably is not very natural for them to answer this question or to give this correct output, because they never train like this format. They train just we need them to remember a large corpus of them. Yeah, so to summarize, why we need adaptation, because the downstream tasks are different. It's probably because of the formatting. So the formatting include like the natural language inference task, the classification, the output format is very different from how the language model to train. So yeah, also like for example, the bird is pre-trained with the mask, but probably in the downstream task, there is no mask in downstream task. So we need a different format to tell the language model, you need to like give a different kind of output and a different kind of input. So probably there are some other reasons like the topic shift and for example, the pre-trained corpus is mostly, let's say it's mostly scientific related, but the downstream task is probably like more other domain, like the literature domain or some others. So art domain. So there are two different, the distribution between these two domains are very different because of the topic shift. So the language model is also like is the same, it cannot handle the different tasks. So also like maybe because the temporal shift, like as the times goes by, so like there is new knowledge introduced in the world, and the pre-trained corpus probably is out of date. And if we want to keep asking the language model like different things, like we need them to adapt to new knowledge. So okay, so this is probably some different reasons. So let's come back to the definition of the adaptation setup. So what so this is actually also borrowed from the Prof. Percy's materials. So what kind of what adaptation it is? So as I draw in the icon, so it's kind of like to add an arm to a robot. So the arm like let it be helpful to make the original language model to more adapt to a specific task. So here the XY is the new specific tasks data set. And usually we term the gamma as the parameter that need to be tuned. So to let the language model adapt to the new data set. So the gamma here, like it can be part of the original parameter family, and it also can be the new introduced parameter, I draw the arm icon. So it's a new parameter introduced. So yeah, but nevertheless, so the final target is to let the robot and probably is a new arm, like the overall new kind of models to be more adapt to the new data. So yeah, so let's start with a relatively easy understanding and the relatively simple and straightforward one. So the probing. So like like what I give an example, the NLI is actually a classification task. So if we want to do a classification task for like given a language model, what can we do? So the most relative, the most straightforward, intuitive idea is, okay, the big language model is so big, I don't want to touch it. I just want to use it. So the most simplest for me method is just to introduce another set of parameter and let it predict what the language model give you. So like I write in this slide. So problem is like usually used for inspecting and understanding the representation of models. So let's say if we have a sentence for text and the language model can give you representation vector, let's say, and we don't know what the representation vector, what kind of information like contained in this information vector. So we can use another prediction layer to predict what the information there is. So let's say if it can successfully be tuned, this kind of prediction head can be successfully tuned to distinguish class A and class B. Then we can say, okay, the original representation must have this information included because it can be totally distinguished with different class. So this is the basic idea. So usually the prediction head, that is the probing head, is usually relatively simple. So they are usually linear or shallow feed-forward network. So which means the probing is do not need so high cost to train or to tune on a new task. So this is most I think is the popular way like for many analysis. So and also the problem is used for like different. It's not only used for BERT like the encoder only model, but it's also can be used for some decoder only model like the GPT or SUS. So, but like I said, so if I give you a sentence like that's a set of text, like I need a representation vector finally, right? But the sentence is combined with like length of L words. So how can we get the final word sentence? Sentence level representation. So there are two very typical ways that you can use. So the first one is use the class CLS, the class token. So that is just plus another specific token into the original sentence and use that kind of token to train to encode the original token. And finally, we expect the special class token can store the sentence level representation in the embedding of class token. And then we can just directly use such class token to do the problem task. So this is predicted by this is published by Devon at 1218. So I think it's still till now is still a very popular method. And also another method is more intuitive. It's just like let's say we have L words, we have L representation vector, we just directly average them. So averaging is can be the final factor of what kind of the average meaning of the sentence it is. So yeah, so this is a two strategy for fixed length representation. So and then for both methods, we can use the probing to give a prediction. So actually, the blue box is the can be trained one or can be tuned one. So and the gray box is not tuned. We do not allow it to tune. So we just need to tune the probing head. So that it is. Yeah. So yeah, I think I mostly done the introduction part, and what we are going to introduce further is like in the adaptation is like what I said in the probing. So we don't want to touch the large language model, the big language model part. But actually, in many cases, we cannot avoid to avoid touching them, because some tasks is like require more domain specific knowledge. So in what follows, we need to introduce like fine-tune tasks. So the first one is the fine-tuning, which will be introduced by Shen and Xiao. And that's why it means we need to fine-tune the parameter from the language model and probably other set of parameter. And also there are more lightweight method. That means, like, let's say there's an original parameter family from the language model as gamma, and we just use the part of gamma, and for example, include the adapter tuning and others, and that part will be introduced by Yanxia and Yajing. Yeah, so that's my part.
So can I ask a question about this? Is it right to say that the point of probing is to figure out a way to represent the new task or the new information in a way that can directly be read by the existing model?
Can you paraphrase the question so that people online can hear too?
So you want
Yeah.
me to paraphrase?
Yeah, you try to paraphrase what Nicholas said, and then
So I'm not 100% understand. So you want to say whether the probing method is used in like more adaptive representation, like can be used for different tasks.
Basically, in a nutshell, what's the simplest way to state the purpose of probing? Yes.
Okay. Also let the online guys hear. So the question is, what's the simplest purpose of using the probing?
Yeah.
So-
because at the start of this section, you see that the purpose of probing is to inspect and understand the parameter, right?
Not instead the parameters, but for example, we have a representation of a word of all of our text. So this parameter, if the language model is fixed, so this parameter is fixed, right?
Yes.
So, but it is a vector. We don't know what the meaning of vector.
Yes.
So let's say we have sentence A and sentence B, then we have vector A and vector B
Yes.
from the language model. So like if we want to distinguish, like, okay, the original sentence, for example, the sentence A have the positive attitude and the sentence B has negative attitude. And if we want to detect whether the representation to vector also store the attitude information, then we just use the fixed representation, that's the two fixed vector, and use another classifier to classify them. If the classifier can like classify them like with very high performance, then we can say like, okay, the extracted representation vector already stored this information.
So basically,
So that is
basically you're testing by putting a new model to the existing embedding,
Mhm.
whether the information that you're getting from your old model can be extracted by a new model, and if so, that means that the vector encodes that information.
yes, yes.
And what does this have to do with the adaptation?
What that to do with adaptation? So I think, from my understanding, this also can be called adaptation, because adaptation, you can use another model to like a plug in to the original model, and you turn the whole model like a new model to the new domain. And this is also kind of adaptation, from general understanding.
I try to
please go ahead.
give an example. Like, okay, let's say for example, there's a certain head in your multi-headed transform, and then we see that if we add an extra layer and we fine tune, and we happen to see that this layer is very good at finding a name entities. Yes, it so happens. Then in a sense, we can say that this layer adapts the transformer to become a name recognition.
Okay, right. Also, that means that when you're doing the probing, the task that you are getting the current embedding to do is not a task that can already be done by existing model. It's just I think it can, or it can, like,
So from my understanding, because mostly because of the format of the input and output. So like let's I still use the original example I give. So let's say there are two vectors. So they already stored this information, but it cannot express like what you expect. So we want to expect the like true false label, but it just can give you two representation, and it cannot like give you some like more
The specific output data.
yeah, right.
I guess because why I'm asking is because earlier on in the introduction, we talked about taking an existing model, changing it. How do you adapt this current model to develop a different task that you could not already do? But then in the presentation on programming, it sounds like this is something that is already existing in the embedding, and you're trying to find a way to extract it. So that means that the missing info is that although it's already the current embedding, the current model is unable to output it the way that you want. Therefore, that is adaptation because we are changing the model in a way that output what you want.
Yeah, I think the following part I include what you want to know. That part includes how to change the original language models parameter and then get the final representation you want. But in this part, I just give out like what I said, the adaptation includes changing the parameter from the original parameter family and probably introduce some new parameters. So this problem part is just using the new parameter for adapting a new task. And yeah, following part like including changing the original parameter families. Yeah.
Sorry, to add on to the question, right? When you mentioned the new parameters gamma, so the gamma are the new parameters of the model that you're planning to get your specific output. Yeah.
Okay. So I want to double check. Is there any other questions?
Any comments about probing? So oftentimes we're using probing to better understand why the model is making the decisions that we want, but it's also something we can use to adapt the models, right? In a very specific targeted way. Any questions? I hope people have questions. Oh, there's some. Are there any questions in the Zoom chat?
Let's see.
Okay, so you asked, hello, LLMs are bad at generalization. How would you address that, Hengchang? Do you think so?
I don't think so. It's related with this. What I present is not related with this question. So I haven't said LLM is better at generation. It depends on the design of the LLM models. So some models are specific design for generation. So what I want to say is that, like, for example, for different generation tasks, like its pre-trained corpus probably is different from what you expect them to generate. Like you want to generate like art related domain, but the training corpus is scientific related domain. So you need to adapt.
Just be clear, Xiao is asking about generalization, not generation.
Oh,
These are two different words.
okay, sorry.
Okay, so we'll come to that shortly anyway. So let's thank Hengchang for his part of the presentation.
I think our next speaker will be present online if I'm not.
No, it's
Oh,
Shen Ting is-
oh,
it's-
yes.
you'll do that.
Sorry,
Yeah.
please.
sorry. Thank you.
Just click on this.
Okay. Right. So for the next part, we'll be talking about fine-tuning for zero-shot learning. It's also known as instruction tuning. Okay. So I think leading on from the question that we had, right, is do language models do good generalization, right? So a lot of times the training data don't really correspond to the tasks that we ask the language model to do. So one example that's given quite commonly is like in one of the papers is say you give a movie review, say Oppenheimer was a fantastic movie, and then you ask the language model, is this good sentiment or bad sentiment?
So that will require a bit more, I guess, context, because movie reviews can, this is a simple one, but if you give it a very complicated movie review, it might not necessarily understand it. Usually, so the conclusion is that, say even up to GPT-3, GPT 3.5, usually you require careful prompt engineering to achieve good results. So personally, I have some experience because recently I'm doing a project where I'm trying to classify survey responses. They're relevant to the questions being asked, right? So you ask the language model, hey, can you classify if this given response is irrelevant or relevant? And then if I try different prompts, sometimes the prompt gives me really good results. Like I say, hey, return relevant or irrelevant. But then sometimes some prompts when you give it just comes out and it gives a whole long paragraph and it doesn't really tell whether it's relevant or irrelevant. So in general, there's this the language models that have been trained have a poor performance at natural language inference tasks. So what is one possible solution to this, which is there's zero shot, there's also few shot learning. So the whole idea behind this is that, say, as humans, if now I have to ask you to do this task, let's say maybe you have never done this before. For example, say the relevant or irrelevant. So I give you a few examples and say this example is relevant and this example is irrelevant. And then based on that, you can usually extrapolate and figure out how to do this. So the question now is, can large language models do the same? So there's this, the first paper is called Language Models, Fine-Tuned Language Models Are Few Shot Learners by Brown in 2020. So the first demonstration they have is that GPT-3 is able to achieve reasonable performance with few shot learning, but it still struggles with some problems. So they then create this new model to build on top of it called FLAN, which stands for Fine-Tuned Language Net. So the main idea is that how do you make a language model better at zero shot learning? Meaning that now I give you the task without any examples, and then the language model can give you the desired answer. So the idea is that you use instruction templates to fine-tune the model. So when you give it, you basically train the model to become better given certain prompts. So if you look at all these templates, the templates are basically curated. You can think of a template as a kind of curated prompt. And then when they train on a whole series of these prompts, they hope to achieve better performance. Okay, so from the paper, this gives an example of what is the difference between the different kind of like paradigms, right? So of course, say BERT or T5, when they do fine-tuning on specific tasks, and then they do inference on the same task. So prompting is that usually you try to use a few shot, giving some examples of prompt engineering, and then do inference on the task. What FLAN does differently is that, so instruction tunes it on other tasks. So let's say you have a whole series of other tasks from B to Z, and you fine-tune all these tasks, and then you do an inference on task A. So the model has actually never seen examples of task A during the fine-tuning process. So it's worth remembering that this is the case of FLAN because there's a slight difference between this and the next paper. And just to say before the question comes, so if you look at this inference on task A, so if I was saying now if I want a FLAN model to do inference on task B, I will then repeat the same process, but I'll fine-tune on A, C, D, all the way to Z. So I do not fine-tune on task B. Okay, and actually, when they wrote this paper, they went even a step further. So they didn't just hold out on the whole, on just a task. They actually define the different tasks into different clusters based on how similar they are, and they hold out the training data for an entire task cluster. And I won't talk too much about results. I mean, suffice to say that obviously they had a positive result. That's why the paper is published. But it outperformed GPT-3 on for zero shot on 20 out of 25 tasks, and it outperformed GPT-3 on few shot learning. So FLAN is 0 shot, but it outperformed a few shot GPT-3 on several other tasks.
So can you say a little bit why they decided to ablate on a task cluster, just so that everyone understands?
Sorry?
Is it because each cluster is a different task?
Yes. So I think they decided that to show that the generalization holds better, they decided to hold it out in the ablation, the whole cluster.
Which studies where they just try to do other clusters, like let's say a task point close to the way to see whether there's any transfer into say that.
So can
Okay,
you
so
paraphrase
the question is, let's say for example, sorry, you said the task from.
So my assumption is that if they train on a different task cluster, and then try to apply that fine-tuned model to a task cluster, maybe they train on paraphrasing, but then they take that paraphrase trained model and apply to sentiment. It probably does not show any results, but is that the case? Is that how it works?
So you're saying that you say you're trying to train on a task that is
Completely unrelated.
completely unrelated.
What they are doing is within the cluster, they train on say on something within the cluster and then test on something else in the cluster, or they train on one cluster and test on another cluster.
Okay. So the question is that do they train on just one cluster and then without one task, and then they perform the test on that, or is it they train on all the clusters without one particular cluster? It's the latter. So they actually train, let's say they train on NLI, common sense sentiment, closed book QA, struct to text translation, and then they don't train on paraphrase, on any of the tasks of paraphrase. Yeah. So it's basically saying that, okay, let's say you have different tasks, but some of the tasks are close to each other. So they decided to make it more fair to say that we don't even train on any tasks that are deemed to be similar to the same task. So in this sense that they are trying to train a model that's generalized to everything else but that task, and then evaluate what's the performance on different tasks in that cluster.
In this diagram, which are the clusters?
So like say natural language inference, they have 7 data sets.
Yeah.
So each of the data sets is a different task.
I see. Okay, so that means that each box is one cluster.
Yes, each box is one cluster.
Are we all clear about this? The idea is that you want a well-rounded learner, right? We always think about that even for when we're educating students, we want well-rounded individuals, not expert in one task, to be able to apply their knowledge to multiple tasks to tackle new unseen challenges before. Like many of us haven't stood in front and gave a YouTube video lecture, but I'm forcing you to do that as part of these sports, right? So that's what we mean.
In the diagram, there's a difference between the blue colors that they indicate.
Just let me double check.
Yeah, if anyone can look on that online, you can answer this question also.
Oh, okay. So what they did is that they further kind of classify. There's a natural language understanding and a natural language generation. So like say summarization, translation, and struct to text, these are considered generation tasks. But the others are considered natural language understanding because you're not generating new material, try to understand what's in the data set. So there's it. So actually it doesn't, it's a good question because the next one, the next paper, that the color actually makes a difference. Okay, so the summary is that they are using decoder only models and they train with a single held out task. So this is the main idea that or task cluster in this sense. So the next paper that
Do you mean evaluated with a single held out task?
oh evaluated, sorry, I'll change this. Yeah. Sorry, I made a mistake.
Okay.
So there's a slightly different approach, which is the next paper that came out a year or two after this, which is called multitask prompted training enables zero shot task generalization. So it's a slightly different approach. Again, they're building on T5. So I mean, in FLAN, they did look at a few BERT T5 and and GPT-3. But in the next paper, they built specifically on T5 to create a new zero-shot model that they named T0. Yeah, so I think they didn't really say too much about in the paper. I don't recall them saying why they call it T0, but I think it's just because they built on T5 and then it's on for zero, it's fine-tuned for zero-shot learning, so they call it T0. So the idea is that they basically train this model on multitask on a few different tasks, and then after that they do a zero-shot generalization. So it's got very similar ideas in that you try to train the model, you fine-tune the model on various other different tasks, and then now you give it a new task to do, and then it will give you the correct answer. Okay, so in this case, it's different from FLAN in that they built a single model. And in this single model, why I say the color now matters is that the ones in yellow are the ones which they train on. So they have a lot of prompts, templates that are based on all these data sets that are in yellow. And then after that, they asked it to do the ones in green. So it's actually quite interesting when you look at the previous one where they talk about NLU and NLG tasks, right? Because things like sentence completion here now it's actually considered NLG task rather than NLU task. Okay, so the other next idea that they have is that they basically try to unify a prompt format for different tasks, and then you can see that some of the examples that they have here. So I won't go too much examples because the paper has a very long appendix. In fact, there's 200 over pages worth of examples. So I would think that it's worth taking a look more into detail if you're interested.
I'd encourage all of you to look through appendices of papers. Sometimes
Yeah.
you can find good patterns where authors try to hide some parts of their details that are actually really crucial. So if you try to replicate a paper without the appendix, it could be very tricky.
So I think like to add on to Prof. Khan's point about the authors hiding or giving details in the papers. These two papers they were listed in the CS324, partially I think also because both sets of authors gave very, very good appendices. Like the FLAN paper has 36 pages of appendices. Yes.
I have a question.
Yeah.
So the question is, what is the difference between the task and task T0 with FLAN?
Sorry?
Like, what is the difference between the task trained for FLAN and T0?
Okay, so the question is, what is the difference between a task being trained for FLAN and T0? So I will probably just jump forward, which is that T0, if you look at the point, T0 trains one model with multiple held out tasks. Whereas what FLAN does is that it trains multiple models depending on what task you're trying to work on. So
yeah, sorry, can I interrupt? So
yeah.
I think, okay, so according to the FLAN paper, they say that they also train one model, right? So the model architecture in our experiments, they use lambda PP against FUI equal to transformer model. So why is there like one people models? So if you go to the paper in the page 4, they say model architecture and we training our experiment with lambda PP against FUI equal to transformer model 137.
Look at the next part where it says the instruction tuning procedure.
Yes, so yes, so the instruction FLAN is just an instruction tune version of lambda.
Correct, but they fine tune they fine tune on different sets of data sets.
We reason so that the difference is that under FLAN, let's say you have 5 tasks ABCD.
Yes.
FLAN will train one model on ABCD for E. Then you train
Yes.
ABCE for D, and so you have like one different model for each task. but that model for that task is trained on everything except that task.
Yes.
While for this T0, it's like let's say ABCDE, they were trained on ABC, and then the model is used for DE.
Yes. Correct. So actually, that's kind of a so the comment was that Flan trains on for task E, Flan will train on ABCD. For task D, Flan will train on ABCE. Okay, so if you look at this, right, on C, it's always they are training on all the tasks except for the ones that you're doing inference on.
Yeah, but this one is the difference in terms of pipeline, like how you design your experiments. I mean, they mix the data set, BCD, and then they include instruction fine-tune on BCD and then inference on task ID, right? Something, that's what you are trying to say. But
Yes.
what I'm trying to say is, what is the difference between the instruction fine-tune data set of Flan and T0? So my question is the difference in the instruction tool data set. Like in this plan they mix BCD, and for T0 they also mix some. So what is the difference between the two?
So what is the difference between the two mix? In T0 they use this set mix.
Yeah, but I mean I saw.
So I think that's incorrect to say that you're asking why, because it seems to you that both of them train on multiple unrelated tasks to do something, right? So therefore,
I mean, but so okay, so India they also cluster into several clusters, and for Flan they also cluster on several clusters.
but for them, the intention, the final model that you run is meant to do one specific thing. For this one, it's supposed to do multiple things.
Yeah, but okay. So according to the paper, what they did was that they picked like random samples from each data set and then they also perform the inference on, let's say you perform inference on that, like, but I also can bring the model inference on that, like that whatever I want. So it kind of like valid. I mean the model, I mean the paper says they did inference on task I, but for me, I can bring the model to inference on other tasks, right?
You can, but that's how they are doing their evaluation.
Yeah. So yeah, I mean, what is the difference between the instruction fine-tune data set of T0 and a Flan?
Oh,
I'm asking about the difference between the instruction fine-tune data sets.
I think he's trying to see that the difference. I think it's the same, like apart from the mixing, right? The multitask and single task help for, right? I think it's the same data set for all 3.0 and 10, like the classes are all the same.
Yeah, the cluster seems a little bit similar, but it should have some kind of difference.
They're written by different authors.
They're written by different authors, so it's
They're not
possible that
using the
they
same
took different open source data set of open source data sets to train.
I think Shenting's point is like that both of these papers are trying to prove the same point. Right? You have multiple data sets, you train for multiple data
Yes.
sets,
Yeah,
you want to generalize.
yeah, I'm trying to find a difference between the two papers.
Yeah, so I think all of us want to know that, right? Because it's very hard to keep apart sometimes why these papers are different.
Yeah. So I'm getting to it, right? It's not so much of the data set. It's like the idea of the idea. I mean the two papers I was up like what Prof. Khan said. The two papers have very similar ideas in that they are trying to find a way to generalize the model through instruction fine tuning. They just have slightly different approaches in how they do the generalization. So Flan, what they do is they do like the whole up all but one, kind of like some kind of like cross validation kind of idea.
I remember that. I mean, I read the two papers, I think two years ago. I remember that there was a difference, but I cannot recall that difference. But yeah, I'm trying to ask you to recall that difference.
It's coming. It is coming.
I think it probably lies in the data set or somewhere else. I remember there is a difference, a critical difference.
Okay,
It's not-
right. So
Yeah.
that one is single task.
That's one aspect.
Yeah,
that has-
one is single task, the other is
But it's not
multitask.
the
That's
only.
only like the experimental design. Can we not say?
Just the like the general, there may be different conflicts in different class level.
Yeah, model. So I think yes, yeah, I think they said something makes sense to me. Yeah, continue.
Sorry. Yeah, well, the other point about that T0 also does a bit differently is that they try to train with a diversity of prompts. So the whole idea is that you want to, it's again back to the generalization idea, right? So flat, you have this very set prompt templates. So what T0 does is that they try to mix it a bit and then see what is the result, what are the results that happens. So the idea now is not just performance that is better than BERT and GPT. I think this is the critical point that Flan doesn't really cover, which is that of prompt robustness, right? Like back to what, yeah.
Yes.
So back to my personal example was that, you know, when I try different prompts with ChatGPT or GPT 3.5, some gives me good results, some give me so good results. So the whole idea now with T0 is that they want to train a model where the results, even if you try different prompts, the results will be more similar and tighter rather than giving too much variance.
Okay, so can I say like T0 has more diverse prompts compared to more diverse, was trained on more diverse instructions compared
Yes.
to that?
Yes, T0 is trained on more diverse prompts. Correct.
Okay.
Or do you want to go back to your chart that you were just showing now?
Yes.
What does P represent here?
Okay, so sorry, trying to not to make the chart too small. So
Does anyone who read the paper remember? You can see on this chart while we're just looking through the text, you know, that the higher P is, the better the performance is. I guess the y-axis here is F1 or some type of performance measure, right?
It's prompts robustness, so it's like the difference in prompts.
Okay,
Yeah.
yeah.
I guess
it's a difference in prompts. So
What does P measure?
Yeah.
So P is the number of prompts on average, and so P equals to 1. Says they have one randomly chosen original task prompt per data set. Wait.
So P equals 0 means 0 shot. I've never seen this before, and I've been.
No. It's the average number of prompts per data set.
Okay, so
Yeah,
P
it's
0
not-
means I have no prompts.
Yeah.
So it's 0 shot, right? P1 means 1 shot. Meaning I only get one chance at understanding what the prompt looks like before you send another one. P equals 8.03 means
On average, you have
see
8.03.
8 variations of the prompt before tackling a new version of this task. Is that right? Generally speaking, so we can see on this chart,
Generally, yeah.
mostly it's upward trends, right? From blue to green. It gets better performance when you expose it to more diverse prompts.
Yeah, so I mean, in the sense that if you go back to this, right, is when they train on all this, the yellow side is they have on average 8.03 prompts for each of them. So this is the one that's probably quite different from Flan, because Flan, I didn't really look in the details, but I would think that it's way smaller, maybe closer to 1, or probably maybe between 1 and 5.7. Okay, so I guess this is like the summary of this section, and also what are the main takeaways we have from this tool, which is that if you do some form of multitask prompted training for fine-tuning, it does improve the zero-shot performance on different tasks, even if the task is different from what it was trained on. So I said before, T0 trains one model with multiple held out tasks. plan just trains multiple models with one task cluster for each. So the next idea is also that the diversity in both and the T0 paper authors, they did both in length and they say creativity. I guess in terms of the language that they use, they give better prompt stability and robustness for the results. Okay, yeah, so this is the end of the zero-shot learning section.
Question, Ting. Thanks for the talk. I have a question about the accumulator. So has the author talked about, or you have some insights about how to combine a set of tasks that can lead a good performance? It's like sort of the curriculum we set for students, right? We have some prerequisite and then learn something other.
Yeah. Okay. So the question is that did the authors talk about how do you set curriculum? So like a set of mix of different tasks to train on. Unfortunately, no. Maybe there are some newer papers that do this.
Okay.
And also given the number of combinations, I guess like this of different types of tasks, maybe if there's no such paper, it might be enough to write a paper. Yeah, but I mean, based on what we've seen so far, probably a good hypothesis is that if you do want to train a good model, maybe you can say take not all the tasks, but maybe you can take like a few tasks from each of the clusters and you train one, and then that should probably give you very good across the board performance. Also probably depends on what is your final purpose. Do you want to do an open-ended language model, or do you want a language model that's very specialized in something?
Thanks for the answer.
Another question? Yeah.
Can you explain what is prompt stability and whether you can measure it?
So prompt stability is well, prompt robustness and prompt stability are largely the same thing. So this is in the paper. This is their idea that if you look at how the results are, like what's the variance between the results of all across all the prompts, then there should be variable. I mean, it can be a bit hard to define because I mean, number of prompts you can come up with is theoretically limitless, right? It depends on, again, like what the authors say, it depends on your creativity.
Okay, so we might define it as variance on what type of prompt is given as input, even though the prompt link belongs to the same class of task. Okay, let's thank our speaker. Okay, before Xiao takes over, I think we need somebody to page
Just
for him. Xiao, are you online?
Yeah, I'm online.
Okay, so Ting will move the cursor and slides for you. Unless you want to try to do remote. I haven't tried remote control before. One thing though, I would like everyone to think about before Xiao takes the floor is that since we're in academia, you want to think about how these experiments with these very large instructions and data sets, how would you try to define this task if you were doing in academia with limited GPU and limited time? Because many of us are students, all of us are doing projects in this course. So you couldn't do T0 or plan as a project. You'd be laughed out because you wouldn't complete even one set of experiments, right? So if you were to do this type of work in academia, how would you scale it down enough so that you can find some experimental results to, teach everyone? Okay, so I want you to think about that. And if you're trying to do things at this level, it just gives you more impetus as a PhD student to argue with your advisor that you should be sent to a very large company for internship, right? Yeah, and earn lots of money, as Michael told us last week. Okay, so Xiao, you can take the floor. You just tell Shen Ting when to forward the slide.
Why not just let Xiao to share your screen?
Okay, can you share your screen instead? Yeah, so you can.
Yeah, But
Yeah.
I need to stop your screen. Yeah. Okay. Okay. So, can anyone see my screen?
Yeah, we can see your screen. You can go ahead.
Okay. Okay, so let me open my video. Okay, so hi everyone, I'm Xiao, a third-year PhD student from Harbin Institute of Technology, and I'm coming to NUS.WING for a one-year visiting program. This part is about fine-tuning, training language models to follow instructions with human feedback. Let's get started. While language models can follow human instructions through instruction turning to some extent. Haskell, LL, from Anthropic proposed the concept of 3H that language models need to realize. Helpful, honest, and harmless. Helpful means that the AI should help the user to solve their task. Honest means that the AI should give accurate information and refuse to answer the unknown questions. Harmless means that the AI should not cause harm to people or the environment by their outputs. For example, the AI that teaches you to make bombs is helpful, honest, but harmful. However, the current language modeling objective that predicts the next token is not inherently aligned with these goals. Thus, language models are misaligned with humans. Hence, OpenAI has built a systematic framework to train the InstructGPT model and also the well-known ChatGPT model. In the beginning, they recruit 40 annotators from Upwork Scale AI. The annotators were screened, onboarded, and extra to annotate the train set. They also recruit different annotators to annotate the evil set without screened to better mirror real world. For the step one, SFT, aka supervised fine tuning. The SFT model aims to predict the completion of given prompt. OpenAI constructed a large collections of prompts from OpenAI GPT-3 playground and annotators. The below three tables show examples, distributions, and number of prompts. The SFT data contains only 13,000 training prompts and many from annotators. For example, ask the language models to list 5 ideas to how to regain enthusiasm for my career. The annotators then demonstrated the desired output behavior of the sampled prompts. The data is used to fine-tune GPT-3 through supervised learning to obtain the SFT model. Okay, for step two, RM, aka reward model. The reward model aims to predict the reward on each completion. OpenAI sampled several outputs from the SFT model. The RM data contains only 33,000 training prompts and many from customers, aka the API only. Each annotator is given 4 to 9 outputs to rank the outputs from best to worst for each prompt. Tiles are encouraged in case where two outputs seem to be of similar quality. RM data is cheaper to collect than SFT data since the annotators only need to give the rank. As shown in the loss function, the left and the right path means the reward on better and the worse completion, respectively. The goal is to maximize the difference between the two selected completions. Especially, each prompt has k completions so that we have CK2 pair to compare. If we sample uniform over every pair from any prompt in each batch, each completion can appear in k-1 gradient updates, which can lead to overfitting. Thus, OpenAI samples the prompt and put all CK2 pairs from the prompt into the same batch. This is much more computational efficient because it only requires k forward passes of the reward model for each prompt. This is why there is the normalization item in the loss. Okay, so I gonna test my presentation in this page, and if you have any question.
Okay, does anyone have questions on this part? Do we all understand the math behind what Xiao said? Like the left side and the right side of this equation. I'd like somebody in our class to try to paraphrase as much as you can guess why this form of the equation looks like this. Warren, go ahead.
The log likelihood of the rewards between like the original model and the new model.
Okay.
Sorry, I cannot hear you so clearly because you were very far from the microphone.
Okay,
Yeah,
so
Can anyone?
You can walk closer.
do you take the log likelihood of like the reward model on the original model as well, then compare it to like the new model, and then you find like how close they are, actually like really the outputs are.
So the question is, I think Warren said, we want to get the good completions closer to the model and the poor completions far away from the model, right?
Yeah, I think something like that.
Okay, so if you look, there's two terms, there's a minus sign between them, right? So the left side is what you are trying to encourage, right? So you're taking a residual between the output of the X and the Y W, right? Which is the encouraged one, and you're subtracting away or whatever the reward is from doing the worst completion, right? So it's a contrasted log. Okay, it's being put through a sigmoid, right? So you get the nonlinearity there, and it's being logged so that you get some logarithmic computation so that you can favor things that are high reward or more, right? And then you have the normalization factor, which is the thing all the way on the left, right? So are we clear about why the small but important detail that's there? Why is it this way that they have K completions? Everyone clear about why there are K completions per prompt? Anyone want to tell me why? Or tell Shashi why there are K completions?
Are you ranking the completions?
We are ranking the completions, right? So it just depends. K is a parameter of the algorithm. We can ask for as many as we want, right? So if you ask for K, then of course it'll have K completions. But the whole point is because there are then choose two ways you can combine any completion against any other, right? That's why we have C2K compares that we could get a complete ranking of, right? So just like if you have a competition, you want to test every player against every other player, then you have that, right? So we don't want to do that if we do it in a naive way, right? So their solution is still to do all of these, but sample from that batch. But more importantly, put all of these pairs in the same batch. Why would we do that? Yeah, but why is it computationally efficient? Okay.
Yeah, so if you push according to the batch, then the sum of the C2 something would be much less than if you put everything in one. Then the C2, the whole thing, the sum would be greater than the C2. Let's say C2K1 plus C2K2 plus until C2KD would be much less than C2K1 plus K2. Yeah.
Okay, so can you give us a more high-level intuition? That's the math, right?
Yeah, so the intuition is now if we have different groups and I only need to pair within the group, but if I put everything the same, I need to pair with all the groups. So all the groups, a lot of more tasks I need to pair. So I need to pair with different groups. So that's why the number is much huge greater than.
right now you're only testing within the group, right?
Yeah,
As compared to, let's say you have a data set of n groups and each group has a few data. So right now this model will just find the pair in between each group, or otherwise it will find all the
Good, yeah, actually, the lab.
Yes, the patch is the group, right? But we want all of the things to be localized in the group so the computation can be just done locally within this group.
Yeah.
We don't have to revisit this group later on in another batch,
Yes, yes.
right? So we just do all the computation at one time, and we say, forget it, we don't need to worry about this update anymore. We've completely forget about these examples. Let's load the next batch of examples in.
I think there's also another important reason for batching it this way, because I think each batch corresponds to a single labeler, right? So if you try to compare a completion from batch 1 and batch 2, if the two batches are different labels, then how can you compare them directly?
Okay, Xiao, did you hear Nicholas's comment?
I cannot hear that the last sentence, just the last sentence.
So he said that I think if we compare cross labelers, these are not comparable, right? If you have different annotators, their rankings are not comparable. Is that what you?
I got your point. I got your problem. That because they for the training part, they actually onboard the annotator, so the annotator will be trained to annotate this data in the way they written in their handbook. So the problem you mentioned that if they annotate the different completion in different scores, which makes the model get confused about the annotation. They try to mitigate the problem in two ways. First, they train their annotators to follow the same guideline, and second, they use the reward function to they try to maximize the difference between the better and worse completions to make the model to understand which one is better. They do not need to predict they do not need to predict the same score as the annotator and annotate. They just need to compare which one is better. It is the most important thing.
Understand that is a problem. I'm just saying that because this is set up to only evaluate within each batch and not evaluate across batches, so then it naturally avoids the problem of annotator differences.
Okay, I think these are good points. We can discuss this in the scribe documents as well. So maybe Xiao, in the time, you can go on.
Okay. Okay, so let me just add one comment here, because actually for this sentence about why this can lead to overfitting, there are several papers proposed by Google or DeepMind. They propose that they found that if you repeat the same data in several times, the performance will degrade. And actually, if you if you sample uniform over every pair from any prompt, that means you just put all the completions in if you have k completions, it will appear in k-1 different batches. So you just repeat the same completion by k-1 times. So it will lead to overfitting and degrade the performance. Okay, so let's go on. Okay, so for the step 3, PPO, aka proximal policy optimization, the PPO model is fine-tuned from SFT model using PPO to maximize the human preference reward from the reward model. The PPO data contains only 31,000 training prompts, and all of them comes from the consumers, aka the API. Okay, so directly using PPO algorithm and the reward model to update the SFT model will bring two problems. First, as RLHF is updated, its outputs become very different from what the reward model was trained on, which caused over optimization of the reward model and worse reward estimation. Hence, OpenAI add a token KL penalty to make sure PPO model output does not deviate too far from SFT model. Second, just using RL objective leads to performance degradation on many NLP tasks. They call it an alignment task. Hence, OpenAI added an auxiliary language modeling objective on the pre-training data to elevate the above two problems. Okay, let's see the loss objective. The first item is PPO loss. The blue item is KL penalty between the frozen SFT model, train on the SFT data, and the PPO model. And the red item is the language modeling objective to make sure the model does not deviate too far from the the language modeling objective just to help the model to prevent the performance degradation on many NLP tasks. Okay, so I just want to pause again at this page because maybe you have any question about the two problems that the OpenAI added the loss item to the PPO loss function. If you have any question, or I will just go on because I only have several pages about the summary.
Any questions from the floor? I think, yeah, we can try to explore these a little bit more in the scribe document if you guys have questions. These are, I think, a bit important because if you understand the ideas behind them and how they get realized into math, you may be able to translate these ideas into your own research area. I mean, this is important, especially for PhD students to see that because the math is designed by people, right? You can decide which ways you want to implement the policy, right? I mean, I shouldn't use the word policy because it's the same as, you know, in PPO, but the whole idea is you design the math to fit the constraints of what you're trying to do.
Okay, so I will go on.
Yeah.
Oh, okay, so this is the whole diagram that illustrates the 3 steps of the InstructGPT model. First, the supervised fine-tuning on SFT data and reward modeling training to get a reward model to predict the each completion to give a score and give the rank result. So the third step is the reverse reinforcement learning via PPO on the reward model. Okay, so let's give a summary of the whole model. The OpenAI first fine-tuned GPT-3 on human demonstrations of prompt completions to get the FCT model. The reward model trained with human feedback or ranking data is not actually used to generate anything, but used to train the PPO and the PPO PTX models. Then OpenAI further fine-tunes SFT model using RL with the reward signal provided by the reward model. A KL loss is provided to prevent the PPO model from deviating far from SFT model. Finally, OpenAI further adds an additional auxiliary language modeling objective on the pre-trained data to elevate the alignment text problem. Okay, so the most important question about the InstructGPT paper in our NLP community that why is RL using human feedback better than we use the SFT data to just fine-tune our GPT-3 model? So the first argument is that the reward is a more nonsense training signal autoregressive loss. If the correct next token is great, the AR loss penalize the prediction amazing, the same as sandwiches. RLHF assigns similar rewards to sequence with similar quality. Moreover, SFT allows only positive feedback, while RLHF allows also for negative feedbacks. We show the SFT model a series of questions and their correct answers, but RLHF model is allowed to generate an answer and get a feedback saying this is not correct. And second, the reward modeling will critical actual completions generated from the model itself, whereas SFT training does not use model generations since it is completely offline. This means the reward modeling may provide more tailored feedback to the model because you will evaluate the generation by the SFT model. Okay, third, the reward model more directly captures the notion of preference. Preference induce rankings, and the rankings can be used to infer preference. Ranking is very naturally captured by the reward signal. The better sequence means the higher reward. In SFT, preference is not explicitly captured since we only train to remember or imitate the best example. And fourth, the reward model is more data efficient. There is a reason why the step one use 13,000 prompts, but step 3 can use 31,000 prompts. For SFT, we need humans to generate target completions. Once we train the reward model, it can be used to score any output. In addition, the prompts are easy to write by humans or even generate by models. So we just write the prompts or generate the prompts and then use the SFT model or the original GPT-3 model to generate the completions, and the reward model can help you to score any output. Okay, the last one is the SFT may teach the model to lie, while RLHF teaches the model to answer or abstain. For knowledge-seeking queries, we expect a truthful or confident answer. We hope the model can say I don't know or refuse to answer in situations that the model the model do not know the answer of the question. The core issue is that we want to encourage the model to answer based on its internal knowledge, but we don't know what this internal knowledge contains. However, whether the model knows or doesn't know the answer, SFT will teach the model to replicate or imitate the given demonstrations. That SFT may actively encourage the model to repeat the answers to make up an answer to unknown questions. In contrast to the supervised setting, the RLHF does not actively encourage the model to lie. The model will get best scores for made-up answers and learn to adopt a policy that relies on its internal knowledge or just refuse to answer. Okay, so that's all. And here I list some useful resources, and I recommend all of you to read the two cases from the Yoav Goldberg. He made some remarks on the large language models and the RLHF for language models. Okay, so if you have any question about this page, you can ask me.
Okay, let's start a hand for our speaker. Xiao is remote because he's in China, so no choice. But I hope all of us preparing for other lectures, especially if you're local to Singapore, please come to give the lecture physically here. Okay. I just want to make it clear a couple things here is that what we're doing in a lot of these cases is doing preference learning, right? So preference learning, we also can call like pairwise learning, right? So everyone is familiar with this. Like instead of just trying to learn one thing, like something is positive or something is negative, right? We are trying to learn the difference between two things, right? This is a ranking model. This is very, very important, especially in information retrieval. You can think about it like if you are doing information retrieval, you want to rank one thing better than another, meaning you have a preference between one page of results with another page. Okay, so a lot of times you want to have this type of differential learning or pairwise learning rather than a learning just for a particular item. Okay, this happens a lot. I'll give you another example that happens in natural language. So in natural language, we have this problem called co-reference resolution. So blah, 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 some sentence, and then you have a pronoun like she said something, okay? Now she can refer to Rebecca or Beth in a previous sentence or anything like that. But if you learn a specific model, say she refers to Rebecca, that doesn't generalize, right? Because what happens if that person is not there, okay? So you often want preferences to say that, if there's another male name in the middle, we disprefer that over a female name in another place, okay? So we want to generalize beyond specific supervised examples. And that's why having this preferential or pairwise learning is very important. You also see this many times as contrastive learning, right? You see contrastive learning means we have something good versus something bad. We want to maximize the discrepancy between these two classes, right? And what Xiao was saying is that if we just do the supervised learning, we don't get that contrastive loss, right? We don't get that pairwise loss. Okay, so that's I think a really important outcome of this. So again, you can bring it back home to your own research area when you think about trying to learn a model, whether you have something that's more of a preferential learning style or you want to actually learn from examples as well. Okay. All right, let's go on to our fourth and final set of speakers. So I think Yanxia and Yajing are coming up. There are some comments there, so thanks, Lawrence, for putting them in. You can put them in the scribe documents as well if we missed those out.
Okay.
Yeah, try again. I think the slide shows at the top, it's just hidden by the tile. Yeah.
Oh,
Is it the
here.
right place?
No.
You have to go farther down, I think.
Yeah.
This platform is the other direction.
Cheers. Pass it, it's fine.
Okay.
Okay. Hello, I'm Yanxia. I'm going to tell you some lightweight fine-tuning method because sometimes we don't want to store one model for each task. We want to save some space and we want to only fine-tune a small amount of parameters.
Let's put it on the screen. Yeah.
Okay, it's some time. I think Hengchang already introduced the lightweight fine-tuning for us. It is also known as parameter efficient fine-tuning. You can search this keyword to find a lot of resources. Mainly, there are three methods: prompt tuning, prefix tuning, and adapter tuning. Oh, sorry. I forgot to tell you that prompt tuning is the prompt parameters that we are going to tune. Prefix tuning and adapter tuning correspond to the lightweight parameters in the figure. I will go with the prompt tuning first. The definition is it's very simple. We just append a soft prompt, some tokens, a vector into the input. It's not some real tokens. It's just a vector correspond to P virtual tokens. If we have input text with its represented as XE and its dimension, it has N tokens and its dimension is E. And we have a soft prompt of PE represented as PE, and it has, I forgot to change the length of the prompt. It should be P. The length should be P, and the dimension is also E. And we can kit them together, feed to a large language model, BART, T5, whatever, and then you can tune with your own data set. The error will propagate and adjust the soft prompt parameters. Okay, the first thing I want, after we introduce what it is, the first question is, does it really work? Yes, definitely. But is it really good? So here, from the original paper of the prompt tuning, they show us a figure that how the performance of prompt tuning compared to one prompt design to full fine tuning. It's called model tuning in this figure. Prompt design means prompt engineering. You change your prompt and you don't tune anything. This is prompt design. Prompt tuning is the soft prompt we mentioned before. I want to remind you of this, the size of these models. They are using T5 for their experiments for model tuning and the prompt tuning. The smallest one, T5 small version, has only 60 millimeters and parameters, and then it goes up from small to base and to large, 3 billion, 11 billion. For prompt design, because we don't use a relatively small large language model for prompt design, we use the biggest GPT-3 for prompt design in their experiments. We can see from the figure, okay, I think prompt tuning is very promising. If I have limited resource, I would try it. Yeah. Okay, from last figure, we know it works, but how should I use it? How to initialize it? And how long should I choose the length of the soft prompt? They do experiments for us. They propose 3 methods. The first one is randomly initialize it. And then the second one is we randomly choose some tokens from the whole vocabulary and then initialize the soft prompts. The last option is we use class labels to initialize the embeddings of class labels to initialize the soft prompts. But if you don't have enough classes, you have a binary classification problem, you have only 2 labels, right? And then you can padding it with random vocabulary initialization. And for how long they tested from 1 and to 5 to 20 to 11 to 100 and then to 150. They also give us an answer, what is the minimal or less? Can I only use 1? That will be very less parameters, right? Okay, let's check out the results. For the prompt length. Okay, here's the result, the figure. For most models, from T5 small to base to large, you must use you must define the length of the prompt larger than 1. At least start from 5. Yeah, 1 doesn't work. But if you have 11 billion per large language model, you can use 1. Yeah. The whole paper mentions you can scale the size of the large language model, and all settings doesn't matter. This is one important takeaway you will see in the future slides. Another takeaway from the prompt length is that if you use the prompt length larger than 20, you will only have marginal gain. So maybe just 20, right? Yeah. So for me, if I'm going to use it, I will first try a length from 5 to 20. Probably 5 first. The second, they compare 3 initialized methods. Yeah, for most cases or most models, random initialization doesn't work at all. Yeah, it's very unstable. But if you have a large, really large language model like 11 billion, yeah, you can random initialize it. But they give us the best solution is start with your class label to initialize the soft prompt first. Okay, now we already know how to use it, but if you are going to use prompt tuning with T5 based model, no, not based T5 based version model, I mean, use T5 as your model, you have one problem to pay attention to is that in T5, they use a span corruption technique for pre-training. But this technique is not helpful. It's not you cannot I think it's from experimental results, it doesn't work. So they proposed, okay, why it doesn't work? Only experimental explanation or observation. Then I want to explain what is span corruption. It is used, here's an example from T5. If your original text is, thanks for inviting me to your party last week, and remember in BERT, we mask some tokens, right? But in SpanBERT, they mask some spans. This is originates from SpanBERT. And then after we do span corruption, the input comes to this span, they replace for inviting with a Sentinel token. Corresponds to, I think, previously mask token we know before. Yeah, and then also they mask another span last with a second Sentinel token. They also have a special end of a sentence token called Z. So after replacing these spans with these Sentinel tokens, we can have our new input sequence into the T5 model. This is the pre-training way used in T5, but it doesn't works very well with prompt tuning. So they proposed some solution for us. Okay, they proposed to use LM adaptation to replace the previous, not replace, it's further fine-tune T5 with language model, prefix language model objective to erase the influence of span corruption. So for comparison, they compared with the previous original span corruption version of T5. Also, they tried to, okay, is it because of in our input, there's no Sentinel tokens? Okay, maybe I can append some to my input and ask T5 to generate output, but it also doesn't work from the result. Let's see the result here. The green line is the language model adaptation way to use T5 as the base model. From figure, we also see some findings. If you have a really large model, again, you can have any settings here. And but if you have a smaller version of the model, we better further adapt the large language model with the language model objective. Oh, they also tried the adaptation steps. I think the similar findings can be found in previous experiments. So I will skip here. Okay, this is prompt tuning. I tell you everything I know, and the takeaway is that if you are going to use prompt tuning, and if you have you are going to try one large language model, right? If you only have resources to use a 100 million size language model, you better fully fine-tune it with your data set. If you have a 1 billion size, okay, you can at least try parameter efficient fine-tuning. If you have more larger, okay, you have more options. But if you have a GPT-3, currently we have GPT 3.5, GPT-4, 5 perhaps on the way. We can use parameter engineering for zero shot. Okay, I want to mention a little bit about the prompt tuning versus other parameter efficient fine-tuning methods. Actually, prompt engineering is not one. It is just I listed here because you may want to, if you have really large, we all have the API to call, right? Maybe you can try prompt engineering for your task first. Here, most people compare prompt tuning versus prefix tuning and adapter, and LoRa is also a kind of adapter way to for parameter efficient fine tuning. From the figure on the right side, we can see, okay, prefix tuning is, we have two parameter matrices. One is appended to the K matrix in the self-attention, or not self-attention, in the attention module. And another matrix is appended to the V matrix. Then this is a prefix tuning. I will introduce how they are combined with the K and V, and how they influence the whole process. I will not mention adapter and LoRa because this is Yajing's duty. You may check here, adapter is put here. After this multi-head attention module or layer, right? And another one is put in. This is the very original adapter. Yeah, there are other variants. There are also LoRa-WING. Okay, prefix tuning, we see that there is an additional parameter matrix called PK and PV, right? Here is referred to PK P and the P value. Let's go back to the most generalized way of attention. it has three matrix, K, V, Q, right? And this is its format. V multiplies softmax of blah, blah, blah. Okay, you can see the equation here. And for self-attention in a transformer, we set these two L at the same, yeah. But in prefix tuning, additional dimension of additional length of K matrix is appended to the previous K matrix and V matrix. We have a new matrix called the K prefix and the V prefix and the prefix, and we are using these two new matrix to replace the old K and the V. Thus, we have a prefix tuning. I think if we are going to program it, it is not very difficult. Not to mention, we have more resources, more Python packages, right? Yeah. These are some references of papers I read for this lecture. And you can also read this. There are many very interesting findings from this paper I didn't mention here. Yeah. And I got some programming or courses for you if you want to know how to use it in your project. Especially the PEFT, I think will include the prefix tuning, adapter, and LoRa, a lot of these methods. Okay, I finished my part. The last part is Yajing. He recorded a video for us. Hengchang, maybe I can just play for Yajing. Do you have any? Maybe.
No, I don't have it.
Maybe before we get to the recorded video, do you guys have questions? Yeah.
Yeah, I have two questions. So can you come to the unify or what it
Oh, sorry, which one? In this one?
Yeah, the previous slide.
Oh, yes.
I have a question about this, but it comes does not allow me.
Yeah, I think it's good to go over this a little bit because I think maybe not everyone understands what all of these things are doing. And what adapters are. Can anyone tell us what adapter, LoRa, and prefix tuning are all trying to do at a high level? Besides Shen, no?
We intentionally insert things of like with in general lesser parameters and we tune those lesser parameters compared to the original architecture, which we might not have the computational resources.
Did everyone get that? Right, so we have a fairly large network with many billions of parameters. We want to adapt it to a task, but we don't want to change all of the parameters because, well, that would overfit, okay, if we have too little. So what we do is we shrink the amount of parameters that's controlling everything, right? So you can think of like, you know, you have like one string to pull a mannequin, right? And it pulls like multiple joints of a figure. So you only have a couple control points, but using those small amounts of controls, you can control the entire figure. So I think of it like that. Okay, so you have very few controls, but you can control many joints at once. So we can think of all of these as something like that. We use a small amount. So what is the difference between adapters, LoRa, and fine tuning? Anyone?
It should be in Yajing's lecture, right?
Okay. So we're gonna come to that. All right. So Yajing is Yajing online?
No, I don't think so. Yeah. She has a
Oh, right. She has the recorded video. So we'll come back to my question after we go to play Yajing.
Yeah, maybe I can play it.
Yeah.
It's 9 minutes, but
Yeah, we'll just go through it. Yeah.
To give an introduction about the adapter tuning. Let's start with the introduction on the tool fine-tuning and the challenges for that. So when we talk about fine-tuning, what we usually mean is to append a task specific layer to the language model, pre-trained language model, and then while this might seem straightforward, this process requires a significant number of model updates, making it resource intensive. And when we are fine-tuning with small data, we may face the issue of overfitting, which causes it to perform well on the training data but poorly on unseen data. And we may also encounter catastrophic forgetting, which is referred to the risk of forgetting the knowledge that the model gained during the training process. And when we are looking at the fine-tuning in various multitask scenario, so for every new task we want the model to perform, we would have to clone the entire model and train it for that specific task. This is both storage and time intensive. Having understood the challenges associated with tool fine-tuning, can we? Is there a more efficient way that we can use to fine-tune the model? Is it possible to fine-tune the subset of parameters by training? And by doing that, we will be able to significantly alleviate storage costs and also tackle the catastrophic forgetting problem. And the solution is called what we call parameter efficient fine-tuning. And here are some examples for it, including first of all the prefix tuning, which adds a tunable prefix token to the input and hidden layers, and also LoRa, which approximates parameter updates using low rank matrices. And last but not least, the adapter tuning that we're going to cover today, which inserts small modules or adapters to each pre-trained layer. This is a quick summary on the different parameter efficient tuning methods. We can roughly group them into 3 types of methods. First one is adaptive methods, which involve adding an extra parameters or even entire new layers to the existing model structure. This model allows flexibility while leveraging the foundational knowledge of the pre-trained model. Secondly, we also have selective methods. So as the name suggested, this strategy doesn't adjust the entire model. Instead, it refines a selected subset of the parameters and enhance the target enhancement, ensure the target enhancement without changing the model structure. Last but not least, we also have reparameterization based methods like LoRa, which reduce the number of trainable parameters by employing a lower rank representation. Now let's look at what exactly the adapter tuning is. So the core idea behind the adapter is to incorporate additional layers, which is named adapter layers, between the pre-existing transformer layers. And these layers act as intermediates, defining the information transfer between the interlinked layers. And by introducing these adapter parameter layers and only fine-tune them for different tasks, we can save, instead of saving a different complete model, we can now save only the adapter parameters for each task. And also the adapter make up only like 3.6% of the model's total parameters, which prove the efficiency and compactness of this method. Now let's dive deeper into the structure of the adapter. It has a 2-layer feed-forward neural network characteristic by a bottleneck, and its output is related to the layer normalization, and it projects the features to a smaller dimensions, and then only bring them back to their original size layer. Two features worth mentioning for this adapter modules. So it has only a few parameters, and during training, we initialize them with a near identity initialization, so that we can have a more stable training process. And then by looking at the experiment result, we also observed that the model performance, of by training using this adapter training is actually highly comparable compared to the full fine-tuning on this global benchmark using BERT large model. And to summarize the benefits of adapter tuning, we observed that it is able to significantly improve the efficiency without compromising the performance. And it also allows flexibility of sequential training without needing simultaneously access to all data sets. And we only add a small number of additional parameters per task, so that is remains lightweight. And then the model still retain the memory of the task it exposes to during pre-training. Yeah. In conclusion, this adapter tuning method only tune the adapter layers added during fine-tuning, and it has a good balance between the model performance as well as the parameter efficiency. Yeah, that's all for my presentation. Thank you.
Okay, so we've come to the end of today's topic. I'd encourage you to spend a little bit of time looking through the different adaptation methods. I think Yajing went into a little bit of detail, but there's definitely more, like what's the difference between LoRa, prefix tuning, where to position of these different layers and parameters, and what effect that has. So the scribing team has about a week to put all of this. I noticed many of the scribes are very active today. That's good. I hope we keep this up for the rest of the class as well. Okay. Again, for those in support, some of you have to be delegated to help out to create the Kahoot for next week. And for those who are in lecture free, please stay back. You may want to check on Slack if there's anyone who's listening but not here to try to figure out the details for that. Okay, so with that, let's thank all of our speakers again. All right, and we'll see you sometime, not clear exactly when, depending on how we end up with the logistics for polling day. Okay, thanks everyone.